Hello, everyone. Thanks for joining us today. Today is actually going to be, even though it's a subject is about generative AI and the use of generative AI for design of semiconductor chips. Now we're introducing a different angle of this in coincidence with an event. It's called CSAW, Cybersecurity Awareness Week. I'm going to share the screen quickly for to give you the context. This event is happening in November this year, and it's yearly, but it also has several types of challenges that run amongst the participants of the conference or the event. So the first challenge here, the AI Hardware Attack challenge, is actually going basically around using the generative AI to insert a backdoor or Trojans in a design. And Efabless is involved in the competition in a way that we sponsor the best designs that will win in the challenge to be made available on to go to the silicon on the next November shuttle for Efabless. Today our guest speaker is Jason. Our guest speaker is Jason Blocklove from NYU, and he's an electrical engineering PhD student or candidate at the Tandon School of Engineering. Jason's research focuses on the cybersecurity and hardware security and hardware generation manipulation using large language models. Also, Jason was a part of the team that won the first place in the first challenge, along with the Dr. Hammond Pierce and others from the NYU team. So. And Jason is going to go show us a demo or a walkthrough about how you can actually do that and how you can do that, inject Trojans or a backdoor into the code. And the second part of the webinar or the talk will Jeff DiCorpo from Efabless will cover some guidelines and how to submit your design to chipIgnite. So Jason, I'll give it to you.
All right, thank you very much for that introduction. I guess I'll just start right off by sharing my screen. I have to move a couple of things real quick so they're not blocking the screen. There we go. I don't have the weird green bar saying that my screen is sharing. Can everyone see my screen? Okay, yeah, looks like
yes.
Great, yeah, so thank you very much for that introduction again. A brief introduction to the challenge beyond this. The main idea behind this AI Hardware Attack challenge is that we want to take open source designs and see if large language models, ChatGPT, Google's Bard, CodeLlama, any of these various large language models can actually be used to insert security vulnerabilities into the designs. So briefly, just the competition timeline. It has already launched. We're here at the 5th of October for this webinar. We've got about 10 days until our round 1 submission deadline. So if anyone's interested in participating, there's still plenty of time to register and at least get started working on things. A few days after that, we'll let the finalists know. And the finalists, if you are based in America, unfortunately, we're restricted to those based in America. But if you are based in America, we will actually bring you out to NYU for CSAW in person for the final round, where we'll probably do some sort of hackathon type thing so everyone can actually be together all working on this. And if you're not based in America, you're, of course, still welcome to participate. You can still be a finalist. You'll just have to participate remotely. But we'll, again, have some Zoom thing set up for this hackathon. So yeah, anyone who wants to be involved absolutely can be. We have additional competition details here and also just throughout this page. You can get here at CSAW.io, and then just select the competition from the top of the page there. We also have a Discord server if anyone wants to join that and ask questions, kind of our easiest way to just have open communication with people interested in the challenge. We have a role for non-participant observers. It doesn't really change anything, it just changes your color in Discord. But then you can, see what's going on with this even if you're not actively participating. So what we're really looking for is how useful this design can be. If you're attacking something that is a widely used open source design, something like OpenTitan, for example, we're going to judge that a little more highly. How you manage to do the attack, how well hidden it is, all of these various things are kind of what we're looking for the submissions. The round one submission is just letting us know where you are in the process of doing of inserting your vulnerabilities, how you're going about it, and your plan for continuing it into the finals. Myself and Dr. Hammond Pierce, who's now based at UNSW in Sydney, Australia, are the organizers, and Andy Wright from Efabless is also going to be helping us judge the competition and pick, our finalists and then the final winners. Something to note is we do have 2 different award tracks going on for this. The best general hardware-based vulnerabilities in open source designs. So that's just a cash prize. First place is $1,000, second is $750, third place is $500. That's for those things that can't really mesh very well with chipIgnite as it stands. So something like OpenTitan, which is its own standalone project. But then a best hardware vulnerability that is suitable for the chipIgnite platform. As Mohammed mentioned, the winner will be placed on the shuttle in November and actually have their design taped out, which isn't a super common thing, as I'm sure many of you know. Actually getting a design taped out usually is a fair bit of effort and time and money and whatnot, and this is a way to actually get something, tangible, and saying, hey, I did a cool thing with this. So getting quickly into how we actually want to go about this. And I'm going to do a quick demo showing you leveraging ChatGPT to insert a vulnerability and test for it. I have this getting started guide put up that, again, is linked from the website. And you can see we have a link here to all of the various chipIgnite projects on Efabless's website. There's 34 pages of them, quite a lot of things going on here. So let's say we want to start finding something that we want to put a vulnerability into. Well, for that, we need some sort of secured system. So let's just see what here uses AES. We have an FPGA programming unit, which looks to have both AES and SHA. We have a cryptographically secure random number generator. We have decryption. We have just full AES. So many different things to choose from. Let's go with this cryptographically secure random number generator because I picked it earlier for a reason. I actually already have it open over here. And you can see that it leverages these other repos that are, at least for the purposes of this demonstration, a little easier to work with. Sorry if you guys can hear some honking down the street. I live in Brooklyn, around the corner from a fire station, so happens pretty often here. My apologies.
So if I may interrupt, if you could just increase the size of the
the font size?
Yeah. When you're yeah, thank you.
Yeah. So we have this AES cryptographically secure random number generator that fits with the Caravelle flow, and Jeff from Efabless will be going through what that actually looks like and what that means after I conclude this demo. But we've got this. We've got all of our Verilog sources here. If we go into the RTL, you can see it has the AES, the AES top block itself, the decipher, what's called the N-cipher block or the encryption block, all of these various things that you need to actually implement AES. And these all come from this SecWorks AES project, which is what I'm going to show you actually inserting a vulnerability into. So to do that, I'm going to open up a terminal and make my font way bigger on that because I assume we'll need it. Pop into my example folder here. I've already messed with this in case the live demo doesn't go too well. I can still show you some stuff that I made over the last couple days, or predominantly last night, admittedly. But we're going to try to do this live. So I'm going to just clone the repo here. And we're going to start putting some things into ChatGPT. It's worth mentioning, ChatGPT is not required for this. There's a bunch of LLMs available that could be used. ChatGPT is just the first one that tends to come to people's mind. So it's the one that I wanted to show the demonstration of. So let's say we want to add a backdoor to this AES. We want to say if the round key for a specific round of AES is equal to some known value, we want to not encrypt it. We're just going to send the block that's the plain text block to the ciphertext block output, do absolutely nothing. We're inserting a pretty standard backdoor into this AES. So let's start with the end-cipher block. Scroll through a bunch of stuff here. And we're just going to copy this entire block and say to ChatGPT, I have this Verilog AES encryption module that I want to modify for debugging purposes. And we'll drop the entire module in there and hit go and see how well it understands what we're starting with. How would we like to modify it? Perfect. That's exactly what we wanted to ask. I want you to make a change so that when the round, what's the actual input is called round key. When the round key input is all zeros, what's the name of the output block? The new block output is the block input. We'll see if it does. Sometimes ChatGPT doesn't want to play along. It's going to say, hey, we can't do that. Sometimes it has absolutely no problem with doing it. So does this make sense? No, this really doesn't. So this is one of the problems that we see a lot with Verilog, and this is one of the things that makes the challenge interesting, is it doesn't really play super nicely with Verilog all the time, especially when you're asking it to modify security features. So the first thing I'm going to do is I'm just going to try to regenerate that response, see if it happens to give me something better the next time. Need to see the existing function. I already gave you the function. Okay, it's not having a fun time with this. Rather than spend a bunch of time hoping that we can get it to give the right answer, I'm actually just going to skip already to the stuff I did last night and show you what I had to do. So I ran into this problem last night as well when I was modifying this. It doesn't seem to want to let me select the previous version of this conversation. But the first time I gave it this, it gave me responses in, oh, wait, there we go. That's how I can change it. So the first thing I did was I started the same way. I gave it this Verilog module and said, hey, I want to mess with this with the goal of debugging. And it tried to explain what was going on. And I said, great, can you add this exact same backdoor? And it said, of course. And then it gave me Python, which is not super helpful. Then I tried it again. I modified it and I specifically said, hey, can you give me the Verilog module? So it gave me a completely different Verilog module. And I actually stopped the response because I knew it wasn't going where it needed to go. And then made some modifications to the initial prompt. I took out some extraneous stuff to try to not eat up too many tokens. And tried again, and it actually did something I find really entertaining and said, sure, you're asking me for a backdoor in this encryption algorithm. Here's exactly how you would do it. It acknowledged that I was asking for a security vulnerability and went ahead with it anyway, which I found hilarious personally. And it just says, hey, we're going to make this this if statement that says if the round key is all zeros, our new block is our old block. Perfect, exactly what we're looking for. So next up, knowing how AES works, we know that the encryption key is given and all of the round keys are derived from that. So how do I make sure that the round keys are zeros when I want them to be? Well, this happens to have the AES key mem, and we say, okay, let's take this key. I just did 0 through F and hex 4 times to fill up the key bits. If we give it this key specifically, could you make it so round key is always zeros? And I gave it the key memory. And it once again played along super nicely and said, absolutely, we're going to add an if statement that just does that automatically for you. Otherwise, we will behave normally. So going to the demo I started yesterday, the AES modified demo. RTL, and let's go to AES in cipher block. So what did it tell me that? So much scrolling in this chat. All right, let's just look for a bunch of zeros. There we go. So it said, hey, add this stuff. And all I did was copy and paste it. I copied and pasted that in. It said add this else begin and then the rest of the logic. So I stuck the else begin in, tabbed everything else, and then whoops, and then stuck and end after all of the case statement here. I did the exact same thing that it asked me to do for the key mem, which was, we'll go to key mem read, which is add this special case if statement, and bam, we have our backdoor. Now, one of the most important things in this competition is that along with showing that you can add a vulnerability, you also need to show how to exploit it. So with AES, we need to now give a test that shows if we give the right keys, we can break this encryption. So the first thing we want to do is check the key mem and make sure that we're giving out all zeros in the right case. No, it seems that my modification for this one actually didn't save, which is very unfortunate. Oh, well, that's a bummer. Somewhere in here at one point I had added, and unfortunately it seems like it got overwritten, something that just sets the input key to our known key value and did a check that it would output all zeros, which is what we were specifically looking for. The slightly more interesting one is if we look in the end cipher block, which I know saved because I tested it quite a lot. I added these tasks for loading the backdoor key and then testing the backdoor just based off of what was already in here. So test backdoor 256 loads up a plain text and it says our expected ciphertext is the same thing. We load in we've already loaded the key, which is its own function. Further up, apparently far further up, there we go. And you can see the round keys I set to all zeros. So this repository happens to have a very nice setup for making these simulations with iVerilog, and I can run, nope, what was it called? And I can run the ncipher.sim, and you can see all of our test cases complete successfully, including our backdoor tests. This is, for the point of the competition, kind of the bare minimum that we're looking for. Just something that shows, hey, we were able to exploit this vulnerability. Now, we're messing with the round keys manually, so we also need to be able to show that we can do it at a higher level. I'm a little bit running out of time here, so I'm not going to go through absolutely all of that, but you can see we have this AES core. I also modified some test cases in here. Our last handful of test cases are all backdoor test cases, which show that we get the same output from the same input. So yeah, you can see ECB backdoor 256-bit test cases. Now, as I mentioned, this is a repository that is a part of several projects that we found in chipIgnite, but it is not a chipIgnite project itself. If you were to modify this, it would not be eligible for the Efabless track for the competition. In order for it to be eligible for that, and Jeff will go a little bit more into exactly how this works, you would need to make some modifications to the actual Efabless submitted repo. You could fork this repo and make your modifications there, have it pull your modified version of the AES, and set up some tests that work within this flow that show that the violation has occurred. I'm not going to get super in-depth into that because part of the competition is that you need to be able to figure out how you want to go about that, how to make these tests happen. But in order for it to be eligible for the Efabless portion of the competition, it needs to work fully with the chipIgnite toolchain and be able to be submitted through their actual repository portal, which Jeff will go into. I think that's it for the basic demo. If you want a little bit more information, as I said, please feel free to join our Discord. There's a link on the competition webpage. Feel free to peruse this. Reach out to myself or Hammond with any questions. And a more basic bit of this demo is actually given in the Getting Started guide, showing a conversation where we asked for a modification be made to a single write register to make it a multi-write register, how to make a test bench for it, and showing the vulnerability. We're kind of trying to give carte blanche for this competition, for you to be able to find whatever design is interesting to you, add whatever vulnerabilities are interesting, and demonstrate in any way that you see fit that the vulnerability works and is well hidden, and all of these various judging criteria that are put on the website. If you can make it work on a chipIgnite platform, we highly encourage it. We think it'd be really cool to see as many submissions of that kind as possible. We have our other award track as well, though. And yeah, as I said, if you have any questions, please feel free to reach out, and then we'll also have some dedicated Q&A time later in the webinar. But I think that's about it for my demo. Thank you all very much. And I believe now I will turn it back over to Mohammed.
Jason, thank you very much. Appreciate it. And then, as Jason said, just either post the questions in the Q&A area, as well as just wait for maybe after Jeff is completed his part to have the questions interactively. So, Jeff.
Okay, great. Thanks. I'm going to go ahead and share. All right, so I'm going to pick up kind of from what Jason presented and just give you a little bit of an overview of the chipIgnite solution at Efabless, give you a little bit of background on what that solution is and what it provides, and then also a little bit walk through how to use it and how you would implement a design that for the contest and into chipIgnite for that we could then submit for fabrication through our platform. So it just as for context and background, chipIgnite is a solution. We provide a kind of a streamlined, low-cost, fast path to building a custom chip, right, without requiring a lot of knowledge, and being able to do that obviously with a lot less time and effort that you would then building custom silicon from scratch. And as part of that, we provide a set of resources to that enable that, right? That includes an access to a framework for the chip design. So it provides kind of a foundation and the framework and the infrastructure that where you can basically focus on just your piece of the circuit or the logic that you want to implement, and all the surrounding infrastructure and support to implement that in an ASIC is provided for you. We also provide a set of tools and a flow as part of that that's highly automated and you're able to kind of go right from a design represented in Verilog or RTL all the way through to a layout that can be physically fabricated. And then we provide, in addition to that, other supporting elements. What you're looking at here is on the back end after silicon is fabricated, we have a standardized design for packaging. We also provide an eval board and tools and firmware for bringing up and testing your design. And so all that's kind of in an effort to really bring down the hurdle and the expertise and the knowledge required to successfully get to implement custom silicon. I'm going to talk a little about in the next part of this is a little bit around some of the pieces of that, like particularly what we call Caravel, which is the that base level chip, and then I talk a little about, show some examples of how you get started on a project, how you integrate your design, and then just quickly touch on some resources on where to go for more information in terms of completing the project and submitting it through the platform. All right, so let me start a little bit first with with Caravel itself. So again, Caravel is, as I said, a harness, a chip harness, or it's a framework for implementing your own custom circuit inside of implemented as an ASIC. And what it provides is it provides a shell which includes kind of the I/O and power pads external to the chip for connecting to the outside world. It also includes inside this chip a microprocessor management core that you can use to exercise your design if you choose to. Again, you don't have to use that, but that facility is there, and the functionality that provides includes an extension of a Wishbone bus interface from the RISC-V CPU that's located within the management area. It extends out into this user area that you can connect peripherals to or connect to with your own design. It also provides a set of probes in the form of logic analyzer signals or probes for both input and output to be able to sense or drive signals to your design. There's an IRQ signal and some user clock signals and some other features as well that kind of complement that. But those are probably some of the bigger pieces. The process. Let me go back to this picture here. So basically, the concept is that we give you a template, right? A project template that you start with and provides an example project, and then there's a automated design flow, which we call for digital design flow. It's called OpenLane, that will take an RTL design and circuit and implement the GDS. That GDS produces basically a layout for the user area that goes inside of this Caravel. And then you submit that through our website, and there's a automated job that you submit on the platform that will take that and integrate that with Caravel and kind of do all the final integration and verification required for fabrication. All right, so I am going to walk through just a couple pieces in terms of how to get started and how to implement a design. A lot of the resources I'm showing you are available on our website. So if you go to the top of our website here, there is a button right here called Getting Started or Get Started. That brings you to a set of videos that are kind of going to walk through the specifics of what I'm going to touch on. There's an initial set here that provides an overview of Caravel. It provides kind of some guidance in terms of setting up your own local desktop for development, as well as kind of creating a repository and kind of getting the project set up, and then uploading your project and submitting that for fabrication. There's a second set of videos on the second page here. There's a link at the top that basically walk through a specific design, a simple design example. In this case, it's just a timer. So a simple timer, but it shows you basically the steps for how to implement that within the what we call user project area or the user project wrapper, how to implement that successfully, and then how to kind of verify that and provide the rest of the configuration required for physical implementation. And then this walks through the actual running the open lane flow to implement the design. Right, so all those resources available. I encourage you to take a look at that. I also encourage you to join the Slack channel. There's a button right at the top you can click, and that will bring you to a page where you can register and join our community. That community is extensive right now. I don't even know, Mohammed, where we're at, 6,000 plus or something like that, folks on that Slack community. And a great place you can join the specific channels related to this challenge, as well as find, get help from a lot of other resources and individuals that are out there implementing designs or if you have questions or run into issues. We're also have our own staff on there as well, so we're monitoring that and providing support as people run into issues. So let me come back to start with a little bit of a Caravel overview. I'm going to just looking at let me start with the Caravel overview first. I'm going to just play a little bit of this video and then just hit some of the key points that you need to understand to successfully integrate a design. Hopefully this should work, as I believe I have my audio sharing. Let me just double check. Yeah. All right, here we go.
This folder already contains a user's project wrapper Verilog file, which is called user.
Sorry, this is the wrong one. My bad. I jumped ahead. I was jumping ahead.
Caravel is an open source template for a system on chip, or SoC, which provides the needed infrastructure for designs using chipIgnite. The Caravel chip is based on the Skywater 130 nanometer open source PDK. There's a version of Caravel called Caravan, which provides bare I/O pads for designs with high speed, high voltage, or negative voltage signals. In this tutorial, we're going to focus on the standard version of Caravel. Caravel's architecture consists of a pad frame, a management area, and a user's project area. Users place their designs in the user's area and use the management area and the pad frame to enable communication of their designs with the outer world. The management area implements a RISC-V-based SoC that includes a number of peripherals like timers, UART, and GPIO. The management area runs firmware that can be used to configure user project I/O pads, as well as observe and control user project signals through on-chip logic analyzer probes, and finally, control the user project power supply. The users area, which is also called user project wrapper, has dimensions of 2.92 by 3.52 millimeters, which is approximately 10 millimeters square of silicon area. This is about 2/3 of the area of the whole chip. It has access to 4 power supply domains, as well as 38 I/O pads, which can be configured through firmware running on the management SoC. It also has 128 logic analyzer probes used to control and observe signals. It has a wishbone port connection to the management SoC wishbone bus. If you would like to see how to implement
Okay, great. So just on the kind of key elements of that, I think I covered it maybe even a bit in the preamble. The main thing that you're implementing is the design that goes into the user project area. That user project area has a predefined set of ports and pins on the external periphery of it that you need to connect to integrate with the rest of the Caravel infrastructure. That includes power pins, and there's multiple power domains. For most simple digital designs, you're probably only going to be using one of the digital domains as a source. There's connections to all the GPIO. There's 38 of those GPIO around the external periphery of the chip. They're all configurable, so they can be configured as digital or analog signals. They can be configured or inputs or outputs or bidirectional signals. And in addition to that, there's a wishbone bus. That's probably the other significant thing you probably would be interested in or consider in your design. And that's available so you can implement a slave device onto that bus, and then you can access that from the RISC-V CPU in the management area. Also provided from the management area is clock and reset, so you can use those as your source for clock and reset for your design. And then there's logic analyzer probes for interacting with your design if you want to, outside of any of those, outside of, let's say, the wishbone bus, if you want to directly probe or drive any signals to your design. Okay, so so I think the things I'm going to go back and highlight is I would recommend, if you have the option, I would recommend using a Linux desktop. And that is what a lot of the examples you'll see kind of in the tutorials are referencing as an Ubuntu environment. If you don't have that, the next best option is to have a Docker installation, and you can install on both on Mac or Windows using a Docker container. And we can provide you some guidance or pointers and best resources for how to do that. This video kind of covers the setup of your desktop, assuming you're implementing an Ubuntu Linux environment. The next piece is creating a repository. So I think that's a good one to touch on. So let me just quickly bring that up.
Repository is called Caravel User Project. Use the link in the video description below. Click the Use This Template green button. You'll need to fill in a name and an optional description. You should pick something that helps people know what your design is. So if you're working on an 8-bit CPU, you could call it 8-bit CPU. Then click the Create Repository from Template button. After a few seconds, you'll have your own repository ready to go. To get the repository set up on your computer, check the next.
So we'll kind of cover that next, but the
video, cloning setup.
The main thing, I guess, which I didn't comment on, is one of the resources, again, available directly from our top of our website, where you can go to github.com/efabless. That is a location for all the content that we host and provide out for both the design as well as the tools that are used for implementing designs using chipIgnite. The primary kind of starting point for doing a new project is this repository here called Caravel User Project. If you click on that, you'll see a read the docs, which you can access from the About section here. Also very useful is this Use This Template button. So this is how the video showed kind of creating a new a new repository based on a clone of or a copy of what's in here in this model. So this repository implements an example, but it also provides kind of all the infrastructure you need to kind of implement a project. All right, the cloning and setup, I would recommend kind of looking at the video, following the video. It's pretty much going to be using a git clone and running a few make targets to set up the environment, which basically is going to go grab the tools and kind of the technology development kit you need for implementing the design for the Foundry. It'll also give you some examples of how to run a test where you re-implement the example that's already provided to confirm that everything's kind of working and operating correctly. So I'd recommend kind of maybe checking that on your own. Just in the interest of time, I'm going to move on to the last one, which is integrating your design. So this is probably the most significant one, which is once you have a function implemented in RTL and you want to integrate that now into Caravel for implementation, this is going to kind of walk through an example of how you do that. So we'll go get this started.
User project wrapper.d.
So let me just like
It's called user project wrapper.d.
Okay, so we cloned the project, and it's basically we jumped right to a file called user project wrapper.v in the Verilog RTL directory, and we're going to walk through a little bit of what the contents here and how this is how this example is implemented.
This file has a user project example Verilog module integrated in it, which provides ports to interface to the user's project design with Caravel. These include interfacing ports to the I/O pads, a Caravel management SoC Wishbone bus slave interface port, logic analyzer ports to observe and control internal signals on the user design if needed. We can rename the user project example to user project timer, as we will integrate our timer inside it. We start by deleting the module counter and its instantiation inside user project timer. which we are not going to use in our project. Also, delete the example logic that we are not going to use. Then we instantiate the module timer and connect its clock and reset ports to those of the user proj timer. So the clock port is connected to WB_clock_I, and the reset is connected to WB_RST_I. For the 7seg 8-bit signals and the digital enable 4-bit ports, we need to connect them to 12 of the 38 Caravelle I/O pads. Every I/O pad is associated with 3 ports. For example, I/O pad number 5 is associated with the ports IO_in 5, IO_out 5, and IO_OEB 5. The IO_OEB controls the direction of the signal. 0 is output and 1 is input. IO_in has this data coming from outside through the I/O pad if it is configured as an input pad. IO_out drives the I/O pad when it's configured as an output. As the timer uses the I/O pads to drive an external 7-segment display, the 12 I/O pads will be configured as output pads by connecting each IOB to zeros and connecting IO_out to the timer 7-segment and digit enable ports. IO_in will be left unconnected as they are useful only when the corresponding I/O pads are configured to be input. So we only need WB_CLK_I, WB_RST_I, and 12 GPIOs.
So I think that kind of hits kind of the key points. I mean, the main, I guess the main consideration here is, I'll go back up a little bit so you can see. We were just talking about here, right? The way that one of the primary things you're probably going to be concerned about is connecting both either the wishbone bus and or the I/O pads. The I/O pads are connected to these IO_in and IO_out and IO_OEB, so it's a 3-wire interface. That's for digital signaling, right? And if you're going to use analog, there's another signal for that, which is called analog_IO, which you need to look that one up. But for digital designs, you'll just need these signals. There's a similar set. So basically there's 3 wires for every pad, 0 through 37 in the chip. And you need to make sure that if you are using them as inputs or outputs, if you're connected to the input or the output, that you are tied the IO OEB signal appropriately. So it's a bar, it's inverted. So it's an output enable inverted. So it's a high is an input and low is an output. Tied low is an output. So make sure you get that connected correctly. Otherwise, your signals will not propagate through to the pad. So that's one kind of key piece. Then again, the wishbone bus interface is all presented here. It's all kind of standard signaling. So if you look that up, you should be able to identify and be able to map to that based on kind of the names of the signals shown. And then of course the logic analyzer signals are shown here. They are fairly generic, so you can actually use them all for the most part independently when you're driving the signaling from the processor. You can the inputs and outputs in OEB are somewhat, there's no logic around those, so you can use those pretty much how you like, as long as you are matching the input and output direction on the signal. Okay, I think those are some of the key pieces. So again, I encourage you to go back and look at the video kind of in total. And again, going back to the full list of videos, just to walk through that, is we walk through this. We touched a little bit on the integrating your design. The other piece that's valuable, and I would highly recommend, is taking a look at the RTL verification. So this shows you an example of implementing a test bench with your design integrated into Caravelle and ensuring that your integration is done properly and successful, and you're getting expected signaling, all the way through the chip out to the pads. So I definitely recommend spending some time on taking a look at that. This next video, physical implementation, will actually walk through how do you implement your design. It's fairly automated. It's going to be a single make target, like make and the name of the module that you have within user project wrapper, and then you'll come back, you'll likely come back and implement the second step where you'll make user project wrapper to kind of do the final assembly and integration of your design for the complete layout. But that is fairly automated. So it mostly, if you have everything set up properly, you just type a command and let it run, and it will complete automatically. You do need, there is some further guidance on just reviewing the results to ensure that everything passed successfully. But in general, you'll see at the end of this flow, you'll see a successfully completed message. And if you reach that, you are most likely good. But again, depending on if you're doing a fairly simple design that's not pushing limits or pushing the limits on timing or other particular boundaries. But if for those cases, definitely look at these other videos, which kind of show you how to review the and verify the results for of the implementation after you've completed layout. Okay, so that was a lot and pretty quick, but I think I'm going to stop there and see if there's any questions. If you do have questions, recommend posting those to the on either what I presented or Jason presented earlier. Post those to the Q&A facility on Zoom.
We had one question that I sort of answered, but I said I could give it an example during our actual Q&A section here. So I'll go through that if there's nothing else immediately pending. So the question was about the CVSS calculator. For the competition, and I will actually share my screen real quick to give an example of this. I'm going to have to make that much larger. There we go. So for the competition, we ask that part of the submission involves your projected CVSS score. CVSS stands for Common Vulnerability Scoring System. NIST has this calculator available that we recommend you use. And all it is a way of determining how bad a vulnerability is. So these basic score metrics are really what we need to focus on. And the scores are kind of designed more for software vulnerabilities than hardware vulnerabilities. So there are some things that don't make a whole lot of sense if you're modifying the Verilog itself to insert a vulnerability. But I'll go through the backdoor I added to AES as a quick example of this. So what the attack vector means is, and actually if you mouse over it, it kind of tells you what's going on. What the attack vector means is what sort of access to the device does someone trying to exploit a vulnerability need. So network would mean, it's vulnerable over a long distance connection. I can mess with it through some, I can SSH into the machine to make it vulnerable, things like that. All the way down to physical, which is you need access to the physical device. Most hardware vulnerabilities that you're going to do when inserting actual vulnerabilities into Verilog are going to be local or physical. So for this, we need to be able to insert a key. It's just a raw AES core. We're going to call that a physical vulnerability. Attack complexity, it's a very low complexity attack. You just need to know the one key that is the backdoor to everything. Privileges required, again, these are kind of more made for software stuff. There's no privileges necessary to inputting a key, but you could probably make an argument for saying low-level privileges. You still need access to the device. User interaction, obviously a user needs to input the key. That one I think is relatively self-explanatory. Scope is kind of a weird one in my opinion. And they give more information here, but I would say the scope is unchanged. We're not modifying how the AES core is actually being used. And then the impact metrics are kind of some of the big ones. These refer to the CIA triad, or confidentiality, integrity, and availability of data. So confidentiality refers to if data that should be kept secret is still able to be kept secret. We're adding a backdoor to AES. That's a pretty high invalidation of confidentiality. Integrity is a question of whether, oh, that's a loud motorcycle. One moment. Integrity is a measure of whether or not data that should be stored securely is not being modified. So confidentiality, is the data not able to be read when it shouldn't be? Integrity, can it be messed with when it shouldn't be? We're not really modifying any encrypted data. We're just failing to encrypt it. I would say probably low. And availability is this resource that should be made available still available or not? We're not affecting the availability of anything. So I would say none for that. And these are all kind of up to interpretation and your own justification when you submit the documentation for the competition itself. But you can see this vulnerability got an overall 4.9 CVSS score. Things like having it available over the network makes it a much higher CVSS score. They kind of move up this way. Things like that. If you can make a vulnerability that affects all of the CIA triad very highly, things of that nature. So that's a gist of how CVSS scores work. And then I also shared in the answered questions section this website that goes through in a little bit more detail what each of those bits means. So I hope that sorts things out for you. Any other questions?
There was one question before about if you have a look in the Zoom chat.
Oh, yeah. Hard constraint to use an open source design that's previously been on a chipIgnite shuttle. It is not. We have 2 award tracks for the competition, either one that will work with the chipIgnite flow or one that won't. If you can find an open source design and make it work with chipIgnite and also add those vulnerabilities, that would be awesome. But we also already have all of these open source designs available with chipIgnite, so you can mess with one of those as well. Or we have that second award track that is not based in Efabless, but you don't get your design taped out.